In this lesson, we're going to continue our discussion of quadratics, and we're going to be taking a look at a particular property of quadratics and the graphs that they form, which is called symmetry. The idea that if you split the graph down the middle, you have a mirror image on either side. So this property, or a parabola, is known to be symmetric, or the property itself is known as symmetry. The axis of symmetry is that dividing line. And the axis of symmetry has some other properties that are quite useful. For example, because of symmetry, the axis of symmetry will be halfway between the zeros. And we can make use of that. And the other thing to keep in mind is that the axis of symmetry matches the x-coordinate of the vertex. In other words, the axis of symmetry goes through the vertex of the parabola. But if we know the vertex of the parabola, we know where either the maximum or the minimum of the parabola is. So we can tie these things together. We can make use of the symmetry of the parabola to find the halfway point, but that halfway point is the axis of symmetry. The axis of symmetry matches the vertex, and from there we end up with what's known as the optimal value, which is going to be either the maximum or the minimum value. So let's take a look at the steps that we would take for doing something like that. Now, in this first example, I'm actually providing quite a bit of the information. You don't have to go entirely from this equation because I've actually provided a computer-generated graph of this same equation. Now, something I want you to focus on here and understand one of the reasons why we're doing this. If you take a look at the graph, notice that the y value that goes along with the vertex here, we can pick out the vertex pretty easily from this graph, but the y value I certainly can't do anything other than estimate what that value might be. I could, of course, also start with the equation here and find the vertex by putting this into vertex form by completing the square. But I did intentionally choose not a particularly nice equation so that I wanted to discourage that. And so instead, let's take a look at the graph. We can see from the graph that we have zeros at -1 and +3. At -1 and +3, I have my zeros. Now that means that my axis of symmetry is going to be halfway between those zeros. So it's going to be the line having equation x equals, and if you don't remember this, it's going to be x equals s plus t divided by 2, where s and t are the zeros of this parabola. So in this case, the s and t values are -1 and +3. So that becomes -1 plus 3 divided by 2. -1 plus 3 is equal to 2, and then divide that by 2 is equal to 1. Now, of course, we could have seen that directly from the graph, but I thought it was worth mentioning this. So from the graph alone, we could have seen that this is our axis of symmetry, and this axis of symmetry has the equation x equals 1. Now that I know that the axis of symmetry is at x equals 1, this also tells me that my vertex is having an x-coordinate of 1, and then it has some y-coordinate. And actually, since we normally represent a vertex using h and k, I'll just go ahead and use the k value there. So the thing we want to do from here is we want to use this x value to find the y value. Because don't forget, no matter what special point or a regular old point that we're talking about along a parabola, all of the points on this parabola have to fit with this equation. So if we're looking for a point that has an x-coordinate of 1, then we can substitute x equals 1 into this equation, and that should tell me the y-coordinate that goes along with this. So I'm going to sub x equals 1 into the equation. In this case, the equation is y equals 2/3 x squared minus 4/3 x minus 2, which is 2/3, but instead of x squared, I'm going to do 1 squared minus 4/3, and instead of x, I'm going to do 1 and minus 2. Well, 1 squared is quite simple. That's just equal to 1. So 2/3 times 1 is 2/3. 4/3 times 1 is minus 4/3. And negative 2, I might want to write that with the common denominator since everything else has a denominator of 3. So I actually might want to write, instead of negative 2 or minus 2, I might want to write that as negative 6/3 so that I can more easily go to my final answer, which in this case is going to be positive 2 minus 4, which is negative 2, minus 6, so that's going to be negative 8, and that's all over that common denominator of 3. So we have an answer. Let's just make sure we're answering the actual question. The question wanted to know the minimum value. The minimum value is the y-coordinate of this vertex, and we have found the y-coordinate of this vertex. So now I know, you wouldn't need to write this in your solution, but I'm writing it here just to be really clear. Now I know that my vertex is at 1, negative 8/3, so therefore the minimum value is negative 8/3. The minimum value is not the entire vertex, that's a point. The minimum value is the number. In this case, it is the lowest number for the y values. So all of the y values up here and all of the y values up here are higher than negative 8/3. Okay, our second example. Find the optimal value of this equation. Now in this equation, I'm not providing you with a graph. I could have, but I'm not providing a graph. What happens if we're starting with just the equation? We're still going to make use of symmetry, and we will start off, once again, this is already in factored form, which means we can take a look at the zeros. Now, I'm going to go into a little bit more detail here. Maybe this is a bit of a review or a reminder. When I want to find the zeros, what I'm really doing is I want to find out where this graph crosses the x-axis. But to cross the x-axis, that means my y value is equal to 0. So if I set y equal to 0, I can find the solutions. It's not a very nicely written word, solve. So then once I set y to 0, I can solve for x. So I get 0 equals negative 35, 2x minus 11, 3x plus 5. So I've got 3 different factors here. 1, 2, 3. So I've got something times something times something else. And the only way that you can multiply things together and end up with a 0 is if one of those things is equal to 0. Now, negative 35 is a number. It already has a defined value. So this can never be equal to 0. So we don't have to worry about that one. 2x minus 11 could be equal to 0. And what value of x makes 2x minus 11 equal to 0? That's going to be x equals 11 over 2. And we do the same thing here. 3x plus 5 can also be equal to 0 for a very specific value of x. So that's when 3x is equal to negative 5, or x is equal to negative 5 over 3. So now I have found the location of my two zeros. And we're going to, just as we did before, now my axis of symmetry is going to be halfway between these two zeros. So the axis of symmetry is going to occur when x is equal to s plus t divided by 2. So once again, we're going to make use of the zeros. So, and it doesn't matter which one you think of as s and which one you think of as t. So I'm going to do 11 over 2 plus negative 5 over 3 over 2. I'm being really careful about how I write this. You could have written this as 11 over 2 minus 5 over 3 right away. That would have been fine. So I've got this whole thing over 2. Rather than work with these large fractions, I'm going to take this idea of divided by 2 and I'm going to move it in front, and instead I'm just going to call it the same as multiplying by a half. And so I've got divided by 2 is the same as 1/2 multiplied by, I've got 11 over 2 and negative 5 over 3, and so that means I actually have a common denominator of 6 for each of those. So what did I have to multiply 2 by to turn it into 6? I had to multiply by 3. And so I have to do that here with 3 times 11, so I end up with 33. What did I have to multiply 3 by to turn it into 6? I had to multiply by 2, and so that means I have to multiply the numerator by 2, and I end up with negative 10. And now that I've done that, I have 1/2, I have a common denominator of 6, 33 minus 10 is equal to 23, and now 1/2 times 23 over 6 is 23 over 12. So I've got an answer here, but this answer is not our final answer. This is the axis of symmetry. But what does the question want? Find the optimal value. So just as I did, it's really no different than what we did before now. Now what I need to do is I need to sub my x value into this equation to find a y value. So y equals, I need to go back and look at the equation again, negative 35, 2x minus 11, 3x plus 5. Negative 35, 2x minus 11, 3x plus 5. And I sub that in, I get negative 35. And this is going to get pretty involved just because this is not a particularly nice fraction. 2 times, but instead of x, I'm going to put in 23. 23 divided by 12. And that is minus 11. And then we've got 3, but instead of x, I'm going to put in 23 divided by 12. And that one is plus 5. And now I've just got to be careful and work with fractions here and get my answer. So the first thing that I would want you to notice is that this 2 goes into 2 once and it goes into 12 6 times. That simplifies things a bit. This 3 goes into 3 once and it goes into 12 4 times. And so that simplifies that one at least a little bit. So now we have, well, this now just stays as 23 over 6 because this is 1 times this fraction. But I should put the 11 over 6, which becomes 66 over 6. For the second bracket, I get 23 over 4 plus, and I have to change to a common denominator, so 5 is the same as 20 over 4. Negative 35. 23 minus 66. So if you're doing stuff like this in your head, you might want to think of it the other way for now. So 66 minus 23, which is equal to 43, but it was going the other direction, so it's negative. So we have negative 43 over 6 in this bracket. And here we have 23 times 20 is 43 over 4 for this bracket. and then to expand the whole thing out. I'm not going to try to do this one in my head because these are getting into some pretty large numbers. Um, is there anything I can do here? Nope, there's no common factors. So 35 times 43 times 43, and that gives us 64,715 over, and now 6 times 4 is equal to 24. And this was negative and this was negative. That's why we ended up with an overall positive. So therefore, the optimal value which in this case, because this parabola opens down, so this optimal value is a maximum, is 64715 over 24, which you might round to. Actually, do we need to round it, or will this be a... Yes, this would actually need to be rounded, so it's approximately 2,696. That's the maximum value on this parabola. Okay, now here's a fairly wordy question, but this is the kind of question where we can actually make use of symmetry quite well. Some of you may have even seen a question like this, or maybe even this exact question. It's quite a common question in quadratics. The city transit system carries 24,800 bus riders each day, and each of them pays $3.15. So the city is trying to get more people to ride the bus, but they also want to make as much money as they can from the bus. So the question becomes, how many people can I get to ride the bus as I change the fare? So they did a survey, and that survey indicates that the number of riders will increase by 800 every time they decrease the fare by 5 cents. So what fare is going to produce the greatest revenue? So the first thing that I like to think of for a question like this, I just want to make sure you understand what we're doing here. So the revenue in this case is going to be equal to the number of riders multiplied by the fare, the cost per rider. Now, when we start, so let's call this R1, when we start, well, how many riders are there? There are 24,800 riders. And what's the fare that they're paying? $3.15. And I find this to be a useful way to set up these questions to help people organize their thinking. What is another scenario that we could have here? Well, this one says that the number of riders will increase by 800. So 24,800, and if I add 800 riders to that, well, what would I need to do to add those 800 riders? I would have to take the price and I would have to drop it by 5 cents. Now I could do another one of these, and what if I did 24,800 but doubled this? So instead I want to add 2 times 800 riders. What kind of price decrease would I have to then implement? It would have to be minus 2 times 0.05. And so now we get to the actual equation, and ideally you want to just be able to go straight to this. You know what, I'm going to number this R0. This was the initial value. So what can I do? I can start with 24,800 riders, and I can add 1 times 800 or 2 times 800 or 3 times 800 or x times 800. Now we don't normally write x times 800 this way. We would normally write that as 800x. And at the same time that I add 800x, I have 3.15 minus 1 times 5 cents or 2 times 5 cents. So that's going to be minus x times 0.05 or 0.05x. And now that I've done this, think about if x is equal to 1 or 2 or 3 positive numbers. This is going to go up and this is going to go down. What if x was a negative number? Then this would become negative 800, negative 1600, etc. This would go down, but if x was a negative number, then this would go up. So this equation allows for the revenue to go up and down, and it allows for increases and decreases in riders and increases and decreases in price. It's just that increases in riders and decreases in price are linked to each other. So now that I've done this, I want to find my zeros. So the way I do that is I set r equal to 0. 0 equals 24800 plus 800x. 3.15 minus 0.05x. You don't have to write out this step, but it does make it clear where this is coming from. This one becomes 24800 plus 800x equals 0. And this one becomes 3.15 minus 0.05x equals 0. X equals negative 24800 divided by 800. And this one becomes x equals 3.15 divided by 0.05. So this is x is equal to, now I'll go to the calculator on this one, 24800 divided by 800. And that's equal to negative 31 because there's a negative sign there. And this one is 3.15 divided by 0.05. And that one is equal to 63. And I'm just going to double check that calculation. Divided by 800, yeah, 31. So now I have essentially my S value and I have my T value. So I can use this to find my axis of symmetry, which is going to be x equals negative 31 plus 63 divided by 2. And then whatever that value is, so this turns out to be 63 minus 31 is 32 divided by 2, which is equal to 16. And now I sub x equals 16 to find my, well, is this what I want? Actually, you know what? I shouldn't get ahead of myself. Always make sure you're checking the question, because the question doesn't want to know the optimal value. The question wants to know what fare will produce the greatest revenue or the optimal value. The fare is this thing, which in our equation is this part of the equation. So that's what we're interested in right there. 3.15 minus 0.05x. So now I'm not actually interested in r. I'm interested in the fare, which is equal to 3.15 minus 0.05x, which is equal to 3.15 minus 0.05, and then I put in 16. So that is 3.15 minus, and then 0.05 times 16 equals 0.8. And so 3.15 minus 0.8 is 2.35. And that's the fare we should charge. Therefore, we should charge, and don't forget to put a dollar sign here, we're talking about money. So we should charge $2.35 for maximum revenue. Okay. Okay, here's another example, a little bit more straightforward in the sense of the equation that's given. So the numbers are not quite so horrendous. And I've provided the graph again this time, but that's because in this case, there's something very interesting. There are no zeros. This graph specifically does not cross the x-axis. So I think it would be a reasonable thing to ask, does that cause us to have to throw away everything? And the answer to that is no. This graph still has symmetry. It's not super easy to see here, but I'll draw a line where the middle looks like. This graph still has symmetry, and we can make use of that by finding what's known as a matching point to any other point that we know. If you take a look at, so here are a couple of points. They are symmetric. Here are a couple of points. They are symmetric. Here are a couple of points. They are symmetric. And in this case, a particularly convenient point is the y-intercept, which is symmetric with its own matching point. So we are going to basically find the matching point to the y-intercept. And what is the y-intercept? That is y equals 7. The y-intercept is the c value when you're in standard form. So how do we find that matching point? Well, we know that other matching point has a y value of 7. So to find that, we're going to sub y equals 7. That gives us 7 equals x squared minus 5x plus 7. So what we're asking is, what values of x have a y value of 7? We have 7 on both sides. They're going to cancel. That means they're going to turn into 0. So we end up with 0 equals x squared minus 5x. This is actually quite simple to factor. It has a common factor here of x and x minus 5. So that occurs when x equals 0 or when x equals 5. And if we look back at our graph, well, that makes perfect sense. When do we have a y value of 7? We have a y value of 7 when x equals 0. And over here, when x equals 5, we have a y value of 7. So these are not the zeros. Technically, these are not s and t, but we can still say that the axis of symmetry occurs at x equals, and however you want to represent this is up to you, matching 1 plus matching 2, if you wanted to say it that way, divided by 2. You don't have to even write this part. You could just say that, well, I understand that this is symmetry, so that's going to be 0 plus 5 divided by 2, which is just 5 divided by 2, which you might write as 2.5. That's a terminating decimal. So this is exact. These are both exact values. What does the question want? The question wants the optimal value. So I have to find the y value that goes with that x value. So now I'm going to sub x equals 5 over 2 into y equals x squared minus 5x plus 7. Let me just make sure that I have it written correctly. X squared minus 5x plus 7. So x squared becomes 5 over 2 all squared minus 5 times 5 over 2 plus 7. 5 over 2 all squared is 25 over 4 minus 25 over 2 plus 7. To put all of this together, I'm going to need a common denominator of 4. So 25 over 4 stays the same. This one becomes minus 50 over 4. And this one becomes plus 28 over 4. And now that I've done that, I have 25 minus 50 is negative 25. Negative 25 plus 28 is equal to 3 over 4. So we end up with 3/4. And since in this case we were given the graph, we can go back and take a look at it. And sure enough, this value, 3/4, that seems to make a lot of sense with the graph that we were given. So we're pretty comfortable and confident in the correctness of that answer. And that is it for this lesson. Now I say that is it. This is not an easy lesson in the sense that some of the algebra was a little bit intensive, but the principles behind it, the idea of symmetry, very important and can be very useful, not just for quadratics, but for any functions that have symmetric properties.